Hello everyone. Glad to be here. It's really good to see a room like mostly full. So it's great. So what I'm talking about today is, I guess the title gives it away, GenStage in the kitchen. So yeah, I mean Keith introduced me. I'll show again this coordinates about me after if you have questions. Or what I do is simple. I work at Erlang Solutions. I work mostly in Elixir. And I try as much as I can to keep close contact with all the development in the community, which is also why I'm talking about GenStage today. There's people from the core team in the audience. I think I saw James beforehand, although I can point it out now. It's good to see also familiar faces. So let's imagine that Johnny, I mean, he's around, but let's like if we can imagine him asking me this question. So what would you like to be if you weren't a software developer? And the answer would be a chef, or at least that's what I like to try to be. It's a difficult job, but I do love cooking. So I'm trying to do the best next thing now, which is basically try to aim to be as good as this person. So if you don't know him, is Massimo Bottura. He runs Osteria Francescana. It's a restaurant in Italy, and in 2016 was voted as the best restaurant in the world. So I said, like, that's ambitious enough. I can try to do that. But as I am a developer, I'm trying like through the back door, which is I'm trying to use GenStage to model a restaurant, where I can point you a little bit on the right-hand corner, simplified version, meaning that the way a restaurant and the kitchen works, it's fairly complicated. It involves a lot of people. So while it's technically possible to build the entire thing, we are going to look at a streamlined version, mostly because otherwise we will need to speak 2 hours. And I'm already sitting between now and coffee time, so I definitely don't want to do that. So before going into the details, let's look at GenStage. Who have never heard about GenStage before in the room? Okay. So GenStage is built to use, basically to shape and model event-driven data flows. So if we look at this example, this is your traditional event-based flow. So you got events coming in your system, and the entity that basically lets this event come in, we're just going to call it producer. Then you have something inside that does some sort of like initial data processing on these events. And at the end of it, you have a consumer. So think about it this way. You get analytics coming in, producer. The second layer is, for example, adding metadata to it. And the third layer, the final consumer, is storing them for long term. Now, in a traditional system, this uses a push mechanism, meaning the data comes in from the outside world, 10 events at a time, let's say, go in, and then reach the consumer. Now, the question is, what happens when the consumer dies or crashes or slows down, even just becomes a bottleneck, effectively? You got a massive queue, and the queue basically means that the layer above cannot push below. So you got a second layer, you start accumulating stuff. But from the point of view of the producer, everything is good. Like, it keeps upset, like that producer keeps upsetting events, they go in. So from the outside world, everything is fine, which is not the case. So for example, if you are consuming data that comes in, for example, through a queuing mechanism, you're going to ingest events. You're going to say, yeah, I know what to do with them. I'm going to process them. And because everything is crashing, most likely they will be gone. So a way to combat this problem, apart from being able to recover this with traditional methods like supervising trees or like things like that, is to shape the problem differently, which is what GenStage does. So switch the perspective around and go to a demand-driven flow, where the innermost layer asks for things to do. The demand is passed back up the stack until it reaches your external layer. And until this happens, until the last demand reaches the producer will keep things that come in at that layer. they will not go down the stack, which means that if the consumer crashes, here things are all good, but up there we start crashing because this, and I'll point here because it's easier than pointing. At this point, we don't have anyone anymore that does the work. Secondly, the producer-consumer doesn't receive a demand, so it stays idle. But because it doesn't receive a demand, it does not demand itself data for the producer. So the producer is accumulating. And at that point, the producer can make a choice and say, OK, I've got too much data. I'm just going to stop accepting events coming in. And you isolate the crash outside the system. How do you handle this demand? The demand in GenStage, this is just like, we're not going to look at everything about GenStage. I'm just giving you the basic coordinates, is that it demands for events. So let's say he asks 5, then it processes 3 and asks for more 2 in the meantime. So it's concurrent in terms of asking for more data and processing data, and it keeps going. And this is what, if you read about it, is the concept of min demand and max demand, which threw me off a bit in the beginning. So that's why I'm mentioning them right here. So the important thing to know is that it optimizes to avoid, why is it not going on? Sorry. OK. Yeah, I'll just press the mouse. It processes while requesting so that no one stays idle. And then no one noticed the typo. Sorry. So let's actually go to the meat. See what I did there again? To the meat of the topic. We are talking about a restaurant. So a restaurant has like some tables. Let's say 4 tables for now, but more than that. And a waiter that takes care of them, or more than one. For all intents and purposes, we're going to focus on one waiter. Then a chef, and after that, line cooks. Now, if anyone has extensive restaurant experience and finds issues with this, please tell me later. Not in the questions, later. But again, line cooks, they worry about a specific type of preparation. So for example, if they're doing grill or they're cooking things in the oven. So they receive only a subset of the orders, just specific dishes, prepare them. And then once that's done, there would be more people involved. They're just going to, in our case, they're going to pass them back to the waiter and say, just put them on the counter. They're ready. The waiter picks them up and gives them back to the table. OK. So if we look at the detail, like just very quickly, the details of the things each component does. So when you're sitting on a table, people take some time to choose the menu. There's always the very slow person that takes ages, that doesn't know what to get, and then you basically tell them, like, get this, because that's good. I was here last time. And maybe you're even lying about it, but it doesn't matter. When everyone decides what they want to get, you just call the waiter. If you're lucky, they're just close by. Otherwise, you signal very visibly. And if they don't show up, we're in a very posh restaurant. Like, if it's the best restaurant in the world, then you have to be a bit posh about it when you go there. So if a waiter doesn't show up in 5 seconds, you just get up and leave. And after ordering, then you're a bit more patient. You wait a good 30 seconds after you order, and they have to deliver you a dish. But as soon as they deliver the first dish, then you can wait a bit more. So even if they bring just one at a time. So all in all, we have some specific constraints about this. Then again, if this expires, if this timeout expires, everyone leaves. The waiter goes around, collects orders from the tables, and then passes them back to the chef. Doesn't do much else. It pretty much just collects things around. When the dishes are ready, it delivers them one by one to the table. We are not going to make it more complicated and collect the orders, just one dish at a time. And the chef, and this is where there's a bit more, I guess, restaurant knowledge, is the chef receives orders and then figures out, in this order, you got 5 dishes, 2 of them go to the line cook that does grilling, 2 of them go to the line cook that does meat, and 1 of them goes for the stews. So in essence, it basically dispatches things as they come in. And each line cook receives a dish request and prepares the dish. And then they just inform the waiter when it's ready so the waiter can pick it up. Okay, so let's go back to that diagram. So once we have this knowledge in, let's think about how we can use the ideas we saw from GenStage to model this problem. So the tables place orders. Now, we don't have control over people on the tables. Like, they just place orders and they call the waiter whenever they like. So we don't have a choice. We have to accept that as a given. So tables are our external border, are events that come in that we cannot schedule and we cannot demand for them. They will just come in. And the waiter just has to collect them. I mean, he's got a thick notebook, so it's going to be okay. But then the chef can start to approach this by demanding things to the waiter. Like, the chef can say, hey, I'm not, like, the kitchen is not ready yet, so please don't come in with your orders. Just keep them there for a moment, like, go around, tell some jokes, serve some wine, here's some bread, like things that you can do just to keep people entertained. But until I'm ready to dispatch orders, don't bring me anything. So the chef demands orders. And we're trying to use here the terminology from GenStage so that we can exactly express that with the right flow. Finally, the line cooks, they demand dishes. Like, they don't care about orders. They care about single dishes. So they ask the chef, you have to give me exactly the things I need to do. So if we see that, then let's look at this from a different perspective. How do we model this with actual dishes? So with a clever use of icons, we have a stew and a steak. And then, for like a fortunate coincidence, those 2 tables are ordering exactly the same thing. But it doesn't really matter. It's just what they're ordering. So in this version of this architecture, we have basically a GenStage flow that starts from the waiter and goes to the line cook. Because, as we said before, we don't model tables through that, because tables are the equivalent of your open socket that lets data in. So tables will use a different mechanism to generate data. But we can start to say, okay, what's a waiter? Well, a waiter, the only purpose of the waiter is just grabbing this data. So in essence, a waiter is a producer. And a waiter is a producer that we can live pretty much with default settings. So it's a producer that uses a broadcast dispatcher. Now, dispatchers are a way that GenStage provides to decide how to fan and distribute work to the subsequent layer. So a broadcast dispatcher gives the same thing, the same event, to all consumers that are attached to it without any specific routing rule. So if you got 3 consumers attached to the same producer and you're using a broadcast dispatcher, they will all receive the same thing. Now, we got only 1 chef, because if you had 2, I mean, it would be a nice restaurant, I think, like, to see how the whole thing goes. But we only have 1. So we're just going to have, we need just a normal broadcast dispatcher. But when the chef demands the orders, the chef does 2 things. First of all, it gets the order and breaks it apart in dishes. So from this point onward, our packet of data is not going to be the entire order of the table. It's going to be 1 dish at a time. Not only that, the chef has to decide who to give the dish. Sorry, I broke that sentence. The chef has to decide the line cook to give the order to. And can I have a small applause for the English? Thank you. Thank you. That was a tricky one. But yeah, so we just do, so the chef is a producer-consumer, which means that it receives data being a consumer, but it also produces it because it transforms it and passes it on. and it uses a partition dispatcher. Partition means, here's the data, I'm going to run a hashing function on it to figure out where it needs to be routed, and then I'm going to pass it on to the right department. In our case, our hashing function is pretty much a lookup in a table. It says, like, OK, this specific dish is a stew, so it's just going to go to a specific line cook. This specific dish is a steak, so it goes to the other one. It can be anything. Depending on the problem, this is something that is left completely to you to implement. As a default implementation, most likely it's not going to be what you need because it's a very domain-specific operation. So our line cooks, they receive the dish they need to prepare. So the first one gets its own stews, and the second one gets steaks. And there are consumers that are set up with a specific partition. So when you boot a consumer and you wanna give it a partition, you just decide it up front. Now this can be done like in different ways. In our case, we know the topology up front of our restaurant, so all of our architecture, so we just decide up front we're going to have one line cook that does this and one line cook that does that. So this is clear. Now, before I mentioned, and this is just like a slightly sort of an aside on what something that I thought it was pretty cool in general in Elixir, just to model something like a table. So a table, each table is a process. And a process, being a table, you can model people deciding just by basically keep passing messages inside a table process. So when you sit down, you can say, OK, this Gen server process for a table starts, and people start looking at the menu. And then when you look at the menu, they schedule a decision, which in our case, it just means randomizing over a range. Which becomes pretty much the time it takes for someone to decide. And then once that time expires, we send a message for a decision. And if we get to the point where everyone has decided, so the number of dishes in the state of the process is the same as the size of the table, then we inform the waiter. Otherwise, we just keep looping. And I think it's interesting how the language allows you to model things like time passing or random events or things like that, things that you could find useful, for example, if you work with hardware and sort of like mocking these type of things. It makes it very easy. So I don't know. I just thought this was nice to share because it's definitely made my life much easier in trying to build this simulation. So we can now look at the relationships between the different components in that simulation. So let's look at how the table and the waiter, how you would model that. And then we're gonna see some method calls, but not big chunks of code, because this is mostly just to give you an idea on how you would model that. But the nitty-gritty details are in a repository, which I may share, although the code is pretty rough around the edges, but we can see that later. So we had constraints around the table. The table was, people were very posh and picky. So they want to make sure that when they ask for a dish, that order is taken seriously up to the point that they want to make sure that it's going to be cooked. So to do that, we can use, for example, a call. So GenStage call, a table calls a waiter with an order, and this pretty much blocks until the waiter can confirm that the order has been processed correctly, meaning it went through the chef and is being cooked. And to do that, we pass back, the waiter calls a reply, and with the reply, he can reply back to the table. Now, this may not be exactly what you want in many instances. Like, depending on what kind of guarantee you want, you may want to use different type of calls if you want to trigger this specific behavior. In our case, I just went for like the most restrictive option from the point of view of giving reassurances to the tables. But the interesting part is that you get to basically move that concern up and down your entire processing line. So then you could, for example, because you get a reference to the table when you call something on a subsequent layer, then you can decide, okay, this is the point in my processing flow when I can confirm that this operation has been successful to the outside caller. Maybe you're going to do extra processing on it, but it doesn't matter. Like, you don't necessarily have to wait until that point. So in our case, informing a waiter requires a reply from the server. Next, and I shamelessly borrowed the implementation of the waiter from one of the main GenStage blog posts where Jose was showing how you would build an event dispatcher, just like a normal event dispatcher, which happens to be very similar to what you want from a waiter. So you can model the waiter as a queue, where you put in an order at a time, and then the waiter goes to the chef, and the chef grabs that order and sorts it out. The interesting thing about this is that, and this is one of the beauty of using GenStage, is that this is completely, first of all, hidden from the point of view of the table and the chef. We're just showing it here, but it doesn't matter. They don't need to know. And the second is that the implementation of these specific bits is left up to you. So you can decide what type of queue you want to use inside a specific point inside a processing line. You don't have to use a queue if you don't want to, or you can slice and return specific subsets of batches the way it works better in terms of performance or patterns. Like, it just really is completely up to the developer in terms of implementation. So in our case, we can stick with a queue. And then the whole thing, how does it get bound together? Like, the chef, to bound together two elements in a GenStage pipeline, the lower level, so for example, the consumer, in our case the chef, has to subscribe to the waiter. The chef has to say, okay, waiter, just like, give me the orders now, I'm ready, like, the kitchen is on. So you can do it asynchronously, because if you put them, for example, inside a supervision tree, maybe you don't need to have exactly confirmation that that process has been completed asynchronously. You can subscribe asynchronously, and your supervision tree will just take care of respawning when things go sour. And how do you model the relationship between a waiter and the chef? It's all done through callbacks. From a point of view, like, a waiter receives a demand, so a waiter has to know how to handle this demand. In a similar fashion, a chef receives events, so the chef has to know how to handle events. So two callbacks are left to implement, and they can be implemented just by saying, okay, in handle demand, I receive a demand, which ends up being a number. So how many things can you process at this point in time? And then you just package that, send them back, and then if you are keeping track of them in the state, because you cannot necessarily send everything you've got down the line. So you just say, okay, I'm going to send you the first two, and then I'm just going to keep these ones for later. And in the same way, the chef receives a variable number of events or orders, and then does some processing. So it says, okay, I'm going to take a bit of time to figure out where they go. And then once it's done, because it sits in the middle, because the chef is a producer-consumer, it will return the data that needs to be passed on. And finally, without any surprises, the line cook binds to the chef. Every line cook binds to the chef with an async subscribe call. So they can say, okay, chef, we are ready to cook. And you implement the same callbacks, except that this time, the chef has to return the right dish. Otherwise, they're not going to be able to cook it. Finally, and this is where this actually Keith pointed this out for me when we talked about it, that it was an interesting thing to talk about. You don't necessarily have to use GenStage all the time, because all of these things are effectively processes that are basically abstractions on top of Gen server, so you can kind of mix and match depending on what makes sense. So in our case, to pass that data back to the waiter, the line cook calls it a cast operation by passing a dish. And this operation, it is provided by GenStage, but it doesn't necessarily return something that by the end of it that goes in the same flow as before, because this is going actually back up in the direction. So we're just, at this point, the waiter handles the cast operation, but does not return anything to push down the line, because this operation doesn't need to trigger any further processing, because it goes back up. But, for example, the table, because it sits outside, the table is served through a normal Gen server. The table is a Gen server, so we just cast with a dish on the table, and the table handles the cast. So you can kind of do mix and match and see what makes more sense depending on what you're building. And it's interesting because you get different constraints and different results. So the demand in this case is, and this is the important thing, is always driven by the line cooks. They are effectively the main, they're potentially the main bottleneck in the operation because they are at the end. So if they can go fast, everything else can go reasonably fast. However, this wouldn't be interesting without a demo, I think. So I just prepared a visual version of this, which I hope can display nicely. Let me just bring it full screen. So this is where I'm going to ask, is this readable enough?
One more.
OK, I'll try one more. Is that better? OK. So first of all, emojis are great to do these kind of things. So this is running, and this is a visualization of that pipeline. That pipeline is just working under the hood. It just gets displayed in this UI every 100 milliseconds, and we get that. So on the left-hand side, we got people deciding. And this is a plate and fork emoji. Yeah, I thought it would be more visible, but it's fine. People decide. They're either waiting with a hourglass or deciding. And then they basically, when you get to the point where the number of dishes is the same as the number of people, the order will be placed. Now, this is a fairly healthy situation in the restaurant because the waiter doesn't have any orders. It pretty much means just writes down the order, walks to the chef takes it, and starts going through the order, and then figure out where things go. And each line in the line cooks is a separate cooking station. So there's nothing queuing. Now, what's interesting, and what we can do with some appropriate buttons, is tweak how things can go wrong in the restaurant. So let's say that the chef gets a paper cut. And can you actually see that number up there? Yeah, because it's cut off on this screen. Now, this takes a bit, because a healthy system, and because we have very generous timeouts on the tables, things will go wrong, but it will take a bit for them to go wrong. So at one point, we will start failing on the left-hand side. And tables will start to pretty much go, just leave. The reason is that chef gets a paper cut button makes the chef much slower than before. So because each dish, to figure out where it goes, it takes a tiny bit of time. If we make it slower, we're going to start to queue. Now the chef is slowing down a lot because he has. Before he was managing to go fast and was doing like one order at a time, but now he's queuing. This means that because the chef is queuing, the waiter is queuing. And the waiter is queuing like crazy, like he's got 12 orders, he's there waiting. It's like, he's also worried, like the manager already has called, he may lose the job, and all of that. Then obviously micromanagement and pressure help the situation. The number of tables lost is skyrocketing. Now, let's look at, like, the interesting part about this is that, let's give a plaster to the chef. Just to show, the chef is good. The chef now, and you don't see it in terms of, you don't see the timeout changing, but the chef is much faster now. The problem is, the system now is basically the failure is just like cascading. There's no, at this point, the system will not recover. We keep losing orders. But because the chef is not fast enough to exhaust the waiter queue. However, this part on the right-hand side, nothing has ever changed for the line cooks. The line cooks have been steadily cooking at the same speed. If that was the most important part in your processing queue, that would have been unaffected. Particularly, they didn't get more load on themselves. Even if now there's a way we can use to restore this situation, but they are completely unaffected. And this is what it means in terms of back pressure. The pressure is not on them, even if this component is misbehaving. The pressure went back up one layer, so the pressure is actually a lot on the waiter now. Poor waiter, like, it's not even his fault. But the pressure is right there. Now, how do we recover from this? The only way we can recover right now is to basically increase the capacity at the line cooks level. Like, we've got a massive queue of events. We know that everything is demand-driven, so we have to increase capacity there to go through the queue. So we can give them an energy drink and make them cook faster. And that will slowly improve things. So if we give them an energy drink, the waiter queue is going to go down. The chef is fast from before because he's got a plaster on. But the waiter, that's what you tell to kids as well. When you put plaster, it's just say, like, now you're good. So that way, you got everything that is slowly going back to normal. Still, the failure rate is not necessarily stopping straight away. We're still losing things because all of the timeouts and all of the things that were open from the tables, they are still there. But this will slowly normalize over time. So yeah, I mean, I trust that this will go down to 0. If you're particularly eager, I can keep it on screen, or like we can do a countdown. Otherwise, I can go on. But yeah, I'll leave it. Yeah. Okay. Yeah. So what should I do in the meantime while we get to 0? Because I got to my last slide, and my last slide is pretty much thank you and things like that. So I don't want to spoil it because I think it's pretty good. But I think it's no. Now, the only thing I hope is that this gave you a good idea on what GenStage aims to do. I realize that the majority of the people will not model a restaurant, which makes me a bit sad, but that's okay. I mean, do analytics or whatever you need to do. Like, everyone has their own job. But in the meantime, let's just take a look at it. It's still experimental, so it's not stable. Things are potentially changing. Depending on the use case, there are also other APIs that you may be interested in too, in terms of wrapping particularly the GenStage part with higher level abstractions. But it's definitely worth looking at. When the videos from ElixirConf Orlando come out, definitely take a look at Jose's talk about it, because it's fairly interesting, and it's got more programming-related examples than mine. But at the same time, I hope they just give you some idea about how things that you can do, like maybe in the gaming space, using GenStage. Yeah, and I'll just bring, I told you that it was, it also looks suspiciously similar to the one that was in the beginning of the presentation. But yeah, so yes, you can reach me at that if you have any further questions, or you can, just have a chat, whatever you like to do. But thank you.
Any questions? There must be some questions.
Yes, there's a person there. As I said before, if you work in a restaurant, please don't do that. Please don't ask me anything.
It's okay, I don't work in a restaurant. Can you, how would you actually notice when one of your stages is not behaving properly so that you could potentially add a new waiter or add a new chef?
So there's a, sorry, it was a bit tongue-in-cheek as an answer, but no, the point is you notice because the tables crash. Meaning it depends on what kind of problem you have. If you have a slowdown, let's say that one of your parts in the processing pipeline is subject to latency because it talks to a database or an external API. And if that latency increases, your response times may grow, but you're not necessarily failing. The point is up to your, at least in the layer above, but ideally in your external border, you should know when things, or you should make a decision on when things are taking too long or when things are may go sour. In this case, the tables have a timeout, 30 seconds, they're gonna basically implode. They're gonna terminate. And that's enough for this specific setup to just basically, they're in a supervision tree, each table, and it just gets respawned. And at that point, this failure rate would be enough, at least in this specific example, to figure out that things are going wrong. Now, this gives you one part of the answer, I guess, which is you know that things are going wrong. In terms of how you decide why things are going wrong, like what part of the pipeline is slowing down, you can either do a bit of instrumentation, check the message queue for each one of the processes. Like it's basically, it's similar. They are processes in the end, so you can debug them in the same way you debug any other process. So by looking at the, possibly trying to trace the state if it grows too much, or check the processing queue in case that matters. Although it depends on how it's set up, because sometimes you just know that their state includes so many events, but the processing queue may be completely fine. So it really depends on what you're looking at. But yeah, you can also reach me out at the booth. I can show you something that definitely helps in profiling this type of problems. Sponsorship plug. Yeah. Sorry, did I answer your question? Okay.
It's quite a quick question, but I'll wait.
I can repeat it.
So you gave there the example of where the table aborts and you've structured it so that the cook is still cooking those orders even though that the people have left, hence why it spools out. How might you, or what features of GenStage might allow you to handle that in a better way? If you, say if the front end notices that the people have walked out and it wants to send that message, you know,
you can cancel
cook.
Demands if you want to. Like you can cancel a demand depending on certain criteria. But so one thing that I didn't do here, which you may need to do.
Could you give some examples of that? I mean, would you use an ID? Because it might be
you can get so in a similar fashion as Gen Server, you get references by the process who performed the, for example, GenStage call. If you do an endo call, you receive the reference of the process. So if I really wanted to, I could possibly just move down the processing line, the reference of the table, and then just do that as a, use that, for example, to route. Let's say you have like two waiters, one collects the orders and one delivers the orders. At that point, you will need that reference to say, okay, this is the table that receives that. You can do it manually, but there are built-in ways to do it if you track process-wise.
It's a fun little app. Have you put it on GitHub, that particular
I will
one?
do that. I will do that, yeah.
Okay, so thank you. Another round of applause, please, for Claudio.